Hi, welcome back to AP Physics C, Electricity and Magnetism, again, Unit 4, looking at magnetic fields. So in this video, we're going to look at torques on current carrying wires. So in the last video, we looked at just what happens when you had just a piece of the wire in the magnetic field. But now let's look at what happens when we have a configuration of wires, right, attached to an axis of rotation. And so what happens, as that, the interaction between that current carrying wire and the magnetic field. Okay, so the most common application of this topic is going to be motors. So motors will use current carrying wires, but they're not going to use long straight wires. They're going to use loops of wires. Okay, now when a current is passed through the loops of the when a current is passed through the loops of the wire, the magnetic field is going to exert a torque on the loops, which rotates the shaft of the motor. Okay, so this is where we have an example of electrical energy being converted to mechanical energy. And so what happens is, if I kind of straighten out I don't want to put it that far up. All right, so if I kind of straighten out my diagram here, okay, my current is going to pass through here, right around my loop. My magnetic field is going to go kind of across my loop. Right, and so because we have a current carrying wire, which is our arrows here, in a magnetic field, okay, it's going to experience forces, okay? And so one thing to note that there is no force at the top, right? Because the current and the magnetic field, right, are essentially parallel to each other. But so all of the force and torques are going to be, in this case, in the vertical pieces. And so if I follow my rules, right? So this is B, my right hand rule, right? And so I'm going to stick my finger in the direction of the magnetic field. And so if I'm looking at the right side where I just wrote that B, the current is up, the force is into the page. Right, now let's look at the left-hand side. Again, B, right? B is going to be fingers in the direction of B, thumb in the direction of my current, and so it's going to be out of the page. So what happens is we have a force pushing this way, a force coming this way, and that's what creates the torque. This motion, right? This constant pushing of this wire, this set of wires, okay, in that manner. Now that we've determined kind of how it does it, let's look at how much, right, torque would be exerted. So again, by using the right-hand rule, we just saw that one force will go into the page on one side, the other force will come out of the page on the other side, which creates a torque that we can use in the equation. So torque, remember, is tau, NIAB, okay, sine theta. So N is the number of turns. It could be 1, it could be 200, it could be 5,000, okay? I is the current. A is the cross-sectional area of the current carrying loops. It could be a circle. It could be, in this case, it would be a square. And then B is the magnitude of the magnetic field strength. Okay, so let's look at an example problem on how this equation works. So here we have, we want to find the maximum torque on a 100-turn square loop of wire of 10 centimeters on a side that carries a 15 amps of current in a 2 Tesla field. So our motor is going to look something similar to what we had on this slide, not so much the picture that I show here, right? So here is what we're really looking at is that coil of wire in there, okay? So the torque is going to be NIAB sine theta. Okay. And so I have, and you can always kind of make the assumption that it's going to be 90 degrees, because if it's not 90 degrees, then you're not going to have any torque. So I have 100 turns. My current is 15 amps. My cross-sectional area, so it is a square of side 10 centimeters, so we would need to convert that to 0.01. So our square would have a cross-sectional area of 0.10 squared. And then our magnetic field strength is going to be 2 Teslas. Okay, and so I plug that into my calculator, and I find that my torque on this current carrying loop of wire is going to be 30 Newton times meters. Okay, to find the direction, we need a little bit more information. Okay, as to the direction that in which direction the magnetic field is going, right, versus the direction that the current is going. So if I'm looking at this kind of configuration where B is going from left to right, I is going up to, this would be our what we had before. So what would that mean? So it would spin in more of a counterclockwise manner. If I reversed my magnetic field, right? So if my magnetic field went the other direction now, but I kept the same current configuration, right? Now it would kind of be reverse. So you would have the out and you have the in here. And so it would spin kind of in that manner, which means it would be a clockwise manner. So to determine the direction that the torque is acting, you would need to know, you would have to have a diagram of what of the setup. Okay. So this in here to the right would produce a counterclockwise, which remember in torque or in rotation is positive, and the other one would produce a counterclockwise torque. All right. So in the next one, in the next video, we're going to look at what happens. So the magnetic fields that surround current carrying wires. Okay. So here we're looking about in these videos, we're looking at forces, torques. Next thing we do is we're going to look at the magnetic field around that wire.